Welcome everyone back to yet another episode of ML Monday. So for the past few weeks, we have gone through the linear regression using Keras linear regressor. We've also looked through CNN to classify our handwritten numbers. And lucky for us, this week will be a non-coding episode where we'll be looking into the code that we have previously written and dive a bit more into the forward propagation, the optimization, and back propagation. So we have a broader understanding of how the machine learning deep neural networks work in real life, why it actually works. So yeah, we will also look into the math aspects using NumPy and see how the nodes are actually represented in numbers and math within the neural network itself. So a bit of multiplication and the basics. On the side note, I've also purchased the online ML course from Datacamp website. So throughout this video, you'll be noticing that I will be referencing the materials from their site. And yeah, hopefully the lecturers over there can provide us with a clearer explanation and help us with our understanding on the terminologies and optimization stuff that we'll be going through today. Let's go!
We'll start by showing how neural network models use data to make predictions. This is called the forward propagation algorithm. Let's revisit our example predicting how many transactions a user will make at our bank. For simplicity, we'll make predictions based on only the number of children and the number of existing accounts. This graph shows a customer with 2 children and 3 accounts. The forward propagation algorithm will pass this information through the network to make a prediction in the output layer. Lines connect the inputs to the hidden layer. Each line has a weight indicating how strongly that input affects the hidden node that the line ends at. These are the first set of weights. We have one weight from the top input into the top node of the hidden layer, and one weight from the bottom input to the top node of the hidden layer. These weights are the parameters we train or change when we fit our neural network model to the data. So these weights will be a focus throughout this course. To make predictions for the top node of the hidden layer, we take the value of each node in the input layer, multiply it by the weight that ends at that node, and then sum up all those values. In this case, we get 2 times 1 plus 3 times 1, which is 5. Now we do the same to fill in the value of this node on the bottom. That is 2 times minus 1 plus 3 times 1. That's 1. Finally, we repeat this process for the next layer, which is the output layer. That is 5 times 2 plus 1 times minus 1. That gives an output or prediction of 9. So we predicted 9 transactions. That's forward propagation. We move from the inputs on the left to the hidden layer in the middle, and then from the hidden layers to the output on the right. We always use that same multiply and then add process. If you're familiar with vector algebra or linear algebra, that operation is a dot product. If you don't know about dot products, that's fine too. This was forward propagation for a single data point. In general, we do forward propagation for one data point at a time. That value in the last layer is the model's prediction for that data point. Let's see the code for this. First, we import NumPy for some mathematical operations. We've stored the input data as an array. We then have weights into each node in the hidden layer and to the output. We store the weights going into each node as an array, and we use a dictionary to store those arrays. Let's start forward propagating. We fill in the top hidden node here, which is called node 0. We multiply the inputs of that weight for that node and then sum both of those terms together. Notice that we add 2 weights for node 0. That matches the 2 items in the array it is multiplied by, which is the input data. These get converted to a single number by the sum function at the end of the line. We then do the same thing for the bottom node of the hidden layer, which is called node 1. Now both node 0 and node 1 have numeric values. To simplify multiplication, we put those in an array here. If we print out the array, we confirm that those are the values from the hidden layer you saw a moment ago. It can also be instructive to verify this with pen and paper. To get the output, we multiply the values in the hidden layer by the weights for the output. Summing those together gives us 10 minus 1, which is 9.
Okay, a quick pause over here as we walk through the video together. So the first thing to note is that this is the same as the y equals to mx plus c example that we've used previously for our linear regression. So in a sense, right now what we have here is the 2 and 3 as our input x, and followed by a single dense layer. So previously in our example, in our coding, we put our dense layer, remember, in Keras. Yep, those are the hidden layers that we have. So each time you put a dense is considered one layer, and the number of node, if like for example, if we were to put 20, then there will be 20 nodes within that single layer. Fun fact, you need 2 or more layers to be considered deep neural network. So yeah, so that's basically it. We pass the 2 and 3 into our hidden layer, which will compute our output of y, which is 9 right now. So far, this is just a single feed-forward in a neural network, nothing fancy, no backward propagation to improve the prediction. So it's a one-way, whatever input goes in, you will have a hard multiplication and addition to reach our final output. In this case, our y of the value 9. Yeah.
But creating this multiply-add process is only half the story for hidden layers. For neural networks to achieve their maximum predictive power, we must apply something called an activation function in the hidden layers. An activation function allows the model to capture nonlinearities. Nonlinearities, as shown on the right here, capture patterns like how going from one child to 2 children may impact your banking transactions differently than going from 3 children to 4 children. We have examples of linear functions, straight lines, on the left, and nonlinear functions on the right. If the relationships in the data aren't straight line relationships, we will need an activation function that captures nonlinearities. An activation function is something applied to the value coming into a node, which then transforms it into a value stored in that node or the node output. Let's go back to the previous diagram. The top hidden node previously had a value of 5. For a long time, an S-shaped function called tanh was a popular activation function. If we use the tanh activation function, this node's value would be tanh of 5, which is very close to 1. Today, the standard in both industry and research applications is something called the ReLU, or Rectified Linear Activation Function. That's depicted here. Though it has 2 linear pieces, it's surprisingly powerful when composed together through multiple successive hidden layers, which you will see soon. The code that incorporates activation functions is shown here. It is the same code you saw previously, but we've distinguished the input from the output in each node, which is shown in these lines. And then again here, we've applied the tanh function to convert the input to the output. That gives us a prediction of 1.2 transactions.
Another quick pause over here. So like what he mentioned, the ReLU activation function is the industrial practice right now. So you can see it almost everywhere. There are also a couple of things that wasn't mentioned. So the first benefit is that the ReLU activation function helps with the reduction of vanishing gradient. So what it actually does is that because everything that is below 0 will be mimicked across, So you won't have a chance whereby the values are round up like sigmoid function to 0 or 1 or the absolute number. The values that are below 0 is actually retained. And also the second benefit is that it has a constant gradient. So what it means that the learning rate will be more consistent throughout. Yeah. So a quick illustration for how activation function works is that, let's say we have a target right on the top and we have a x that travels only at a straight constant line. It will never meet the output that we want. You will never be able to predict it. So what the activation function does, right, it acts as a ramp or slope for you to reach the eventual output right at the top. So if with enough sort of activation function or ramp, we can actually translate that into any target. So essentially what it means that with enough activation function and your weights, you can actually reach all permutation. Yeah, that's right.
The difference between modern deep learning and the historical neural networks that didn't deliver these amazing results is the use of models with not just one hidden layer, but with many successive hidden layers. We forward propagate through these successive layers in a similar way to what you saw for a single hidden layer. Here is a network with two hidden layers. We first fill in the values for hidden layer 1 as a function of the inputs, then apply the activation function to fill in the values in these nodes. Then use values from the first hidden layer to fill in the second hidden layer. Then we make a prediction based on the outputs of hidden layer 2. In practice, it's becoming common to have neural networks that have many, many layers. 5 layers, 10 layers. A few years ago, 15 layers was state of the art, but this can scale quite naturally to even 1,000 layers. You use the same forward propagation process, but you apply that iterative process more times. Let's walk through the first steps of that. Assume all layers here use the ReLU activation function. We start by filling in the top node of the first hidden layer. That will use these two weights. The top weight contributes 3 times 2, or 6. The bottom weight contributes 20. The ReLU activation function on a positive number just returns that number. So we get 26. Now let's do the bottom nodes of that first hidden layer. We use these two nodes. Using the same process, we get 4 times 3, or 12, from this weight, and minus 25 from the bottom weight. So the input to this node is 12 minus 25. Recall that when we apply ReLU to a negative number, we get 0. So this node is 0. We've shown the values for the subsequent layers here. Pause this video and verify that you can calculate the same values at each node. At this point, you understand the mechanics for how neural networks make predictions. Let's close this chapter with an interesting and important fact about these deep networks. That is, they internally build up representations of the patterns in the data that are useful for making predictions. And they find increasingly complex patterns as we go through successive hidden layers of the network. In this way, neural networks partially replace the need for feature engineering or manually creating better predictive features. Deep learning is also sometimes called representation learning because subsequent layers build increasingly sophisticated representations of the raw data until we get to a stage where we can make predictions. This is easiest to understand from an application to images, which you'll see later in this course. Even if you haven't worked with images, you may find it useful to think through this example heuristically. When a neural network tries to classify an image, the first hidden layers build up patterns or interactions that are conceptually simple. A simple interaction would look at groups of nearby pixels and find patterns like diagonal lines, horizontal lines, vertical lines, blurry areas, etc. Once the network has identified where there are diagonal lines and horizontal lines and vertical lines, subsequent layers combine that information to find larger patterns like big squares. A later layer might put together the location of squares and other geometric shapes to identify a checkerboard pattern, a face, a car, or whatever is in the image. The cool thing about deep learning is that the modeler doesn't need to specify those interactions. We never tell the model to look for diagonal lines. Instead, when you train the model, which you'll learn to do in the next chapter, the network gets weights that find the relevant patterns to make better predictions. Working with images may still seem abstract, but this idea of finding increasingly complex or abstract patterns is a recurring theme when people talk about deep learning.
Alright, we have made it to the end of this week's video. As usual, please help my channel grow by smashing the like button below. Yep, and I will see you next week. Goodbye.